we know how to take derivatives of functions. If I apply the derivative operator to x squared, I get 2x. Now, if I also apply the derivative operator to x squared plus 1, I also get 2x. If I apply the derivative operator to x squared plus pi, I also get 2x. The derivative of x squared is 2x. Derivative with respect to x of pi of a constant is just 0. The derivative with respect to x of 1 is just a constant. It's just 0. So once again, this is just going to be equal to 2x. In general, the derivative with respect to x of x squared plus any constant is going to be equal to 2x. The derivative of x squared with respect to x is 2x. Derivative of a constant with respect to x. A constant does not change with respect to x, so it's just equal to 0. So you take the derivative, you apply the derivative operator to any of these expressions, and you get 2x. Now let's go the other way around. Let's think about the antiderivative. Antiderivative. And one way to think about it is we're doing the opposite of the derivative operator. In the derivative operator, you get an expression and you find its derivative. Now what we want to do is, given some expression, we want to find what it could be the derivative of. What it could be the derivative of. So if someone were to tell you, or give you 2x, if someone were to say 2x, or let me write this. So if someone were to ask you, what is 2x the derivative of, they're essentially asking you for the antiderivative. And so you could say, well, 2x is the derivative of x squared. You could say 2x is the derivative of x squared. But you could also say 2x is the derivative of x squared plus 1. You could also say that 2x is the derivative of x squared plus pi. I think you get the general idea. So if you wanted to write it in the most general sense, you would write that 2x is the derivative of x squared plus some constant. So this is what you would consider the antiderivative of 2x. Now that's all nice. But this is kind of clumsy to have to write a sentence like this, so let's come up with some notation for the antiderivative. And the convention here is to use kind of a strange-looking notation, is to use a big elongated s-looking thing like that, and a dx around the function that you're trying to take the antiderivative of. So in this case, it would look something like this. This is just saying this is equal to the antiderivative of 2x. And the antiderivative of 2x, we have already seen, is x squared plus c. Now, you might be saying, why do we use this type of crazy notation? It'll become more obvious when we study the definite integral and areas under curves and taking sums of rectangles in order to approximate the area of the curve. Here, it really should just be viewed as a notation for antiderivative. And this notation right over here, this whole expression is called the indefinite integral. The indefinite integral of 2x, which is another way of just saying the antiderivative of 2x.